That's just a button.
Yeah.
Press.
Yeah. And so now you're live.
Okay.
Thank you.
Thank you. All right. Please don't. Do we have any water? Yep.
Where'd you get that water for?
I don't know. They had like little cups before. You can go check it out. Sure.
Oh, seriously.
Yeah, just go THP.
Yeah, I think it's still up your bottle.
All right. Is this thing on? Yeah, a little bit. Hey everyone, how y'all doing? Yeah, I'm about ready to get started. I was just trying to find some water, since that's an important part of public speaking. I think it's on its way. So, give everyone a chance to get settled down and get started in about 2 minutes or so. Or whenever it gets quiet, you know.
Can you make the fonts of line text bigger?
I can make it so much bigger. How are we doing there? Just about. Cool. Code is very little of what we're going to be looking at, but we are going to be looking at a little bit of code. What's up, Matt? I think just saying hi. Hello. Great. How's everyone doing? Good? Awesome. Cool. Okay. You guys are a lot more talkative than our last presentation, which is great, because I'm going to ask a lot of questions, and I'm hoping for a lot of interactivity here. So to begin with, who is here because they're curious about what AWS and what it does, and who is here because they kind of have used AWS and they want to use it better? Cool. All right. Good. Good and perfect mix. That's really good to hear. So you know, honestly, AWS is you know, if nothing else, right? It's huge. So you know, here we are looking at the full set of things that you can click on in the Amazon GUI. I want to give a little bit of background in terms of my own onboarding onto AWS, just so you know sort of who I am and where I come from. So my name's Sasha. I'm the director of web development at Fuzz Productions. We're a company that specializes in developing mobile applications and front ends. So what that means is that in particular we do a lot of API and web service development, and we deal with a lot of traffic. How much traffic? You know, an example and something that we're sort of going to delve into in general is an infrastructure that we have sort of perfected at this point, which is a EMAG OS that we use for newsstand applications. This is a rough schematic of what it actually looks like. What you'll see is that we basically have a cluster where we have varnished API servers that are load balanced that do things such as verify receipts for people who have entitlements to subscription products, doing two-way communication, writing to a DB master and reading from DB slaves, pushing jobs into queues that do things like subscribe people for push notifications and use S3, which is Amazon's storage service, and a content delivery network for syndicating the actual content. And using a CMS that sort of like shepherds the content into there and initiates the push actions. So these are the typical tablet and iPad and Android tablet newsstand applications that you will see. where you essentially have like a digital magazine subscription. And the way that we manage the content is more or less this. Who is already lost and would like me to slow down? Just get a sense of it. Okay, that's good. That's few enough people for me to sort of keep going. But to back it up for a second, what we're looking at is essentially a distributed architecture for hosting a big backend. Some of the things that go into making what we would call a backend big, load, that's just how many people are using it. Concurrency, which will say how many people are using it at the same time in particular. In particular, the clustering of those concurrent events, that's not good, that essentially results in what we might call a sort of like data bomb that happens periodically with apps, especially apps like this. So for one that we rolled out relatively recently, one of the really interesting things that happened there was we encountered a system whereby we were migrating a legacy newsstand app, and Fuzz had sort of taken over the code base and re-implemented it. And it had a really unique sort of situation whereby they were guaranteed to be 40,000 subscribers out of the gate. So we did a forced update to the iPad app. That means that basically we woke up the morning we launched the app and there were 40,000 people who were paying customers who wanted their issue of the day's newspaper. The way that these push services work, Apple's really particular about how it lets you send push notifications that wake up an app in the background. Android is kind of like the wild, wild west in more ways than one, but especially with regard to push notifications, you can really send a push and wake up an app at any time for any reason, and there's no default behavior there. Apple has a special content available push that's allowed for newsstand apps that are published in Newsstand, and only those are allowed to wake up the app and start downloading the issue or really execute any code in the app, and only once every 24 hours. So they have strict guidelines around how that can be used. So what happens when this push goes out? What happens essentially is you send out push notifications to 40,000 devices. 40,000 devices within about 1 minute of each other hit your API at the exact same time. They say, am I subscribed? If so, give me the issue content. So who has ever dealt with load like that? Anyone? A little bit? Yeah? Little bit of like 40,000 requests in the same minute?
Sometimes bigger, sometimes smaller.
Sometimes bigger, sometimes smaller, right? So like the first thing that you think is like, wow, like how am I going to do this? Like especially when you have like a batch of database reads essentially. Yeah. In some cases, you have people who have expiration dates in the past, but you don't know if you verified their in-app purchase. So what you need to do is essentially send them their receipts up to be verified with Apple and see what their latest expiration date is. How we accomplish that is, like by a system of essentially horizontal distribution of load. AWS will let you pay more for more resources on a single machine, but you will get to a point where vertical scaling is not the answer that you need. And you will get there relatively quickly when you're looking at that kind of load, especially if you're using applications that are not necessarily optimized for that kind of load. So, what I'm going to walk you through is really the way that you can set up a system like this without going too deep into the application code. I've really just, mocked out some stubs for how things might work. And I will be walking you through the details of how it can be implemented on AWS's infrastructure. Yes, sir?
Wouldn't it have been simpler from the start instead of sending out 40,000 push notifications at once to batch them?
Simpler from the start, yes. Meet the business requirements, no. Newspapers in particular, they're old technology in a lot of ways, but they have some very antiquated ideas about how content distribution strategies should work. Among many of those is the idea that there's a publish button, and then you just send it to the press, and then you can start delivering them in batches. So basically, the contract states that this is how they want it to work. This is what customers are used to. They wake up in the morning and the issue is there. Another thing to point out is that the way Apple's push notification service works, and in many ways the Google device messaging as well. Has anyone worked with it at all? Native app messaging. It's real special. So we all use HTTP, to make requests, which is essentially a connection over TCP that sends specially formatted strings that we call headers. And uses DNS and other facets of TCP/IP to route requests to the appropriate place and interpret them on the server side. TCP is the socket level connection essentially, which is a robust and reliable way to transmit content and ensure that it got there. The way that push notification works, and I can't really tell you why, but this was an early implementation decision by Apple, is so low level that you're interacting with sockets and not interacting with HTTP requests. So basically, a device sends you a push token, and that push token is unique to the device, and it helps use the push protocol that eventually finds you. For Apple, it's APNS. For Google, it's device messaging, cloud messaging, Google Cloud Messaging Service, or GCM. For Amazon Kindles, it's ADM, which is Amazon Device Messaging. Those are all separate and proprietary protocols, but they all work basically the same way, both for subscribing and for pushing out. And for subscribing in particular, what you do is you take essentially a batch of push tokens and you open a socket level connection and you just pump the tokens into the connection. The way you know that you screwed something up is it closes the connection prematurely and you stop being able to send data. So when you build a system that does that, one of the things you have to be aware of is exactly where you were if you get broken off for any reason. So it's a horribly complicated system, needless to say. That's why we're really glad that AWS solved all of those problems for us. So one of the push services that we use is SNS, which is Amazon's simple notification service. It makes a REST API in front of this functionality so we don't have to deal with it. Following that, basically everything is a queued message, and that queued message essentially makes its way into their distribution centers and does send them out incrementally, so not all at once, because that would be, impossible for them essentially to handle that kind of, situation anyway. But it is fast enough that they can send 40,000 in a minute, and that's the situation that we find ourselves in, which is good because they want everyone to have the issue by 5:05 a.m. downloaded from the cloud, and they want to send the push at 5 a.m. So I hope that sort of answers why we didn't do it the right way, right? Or the way that anyone would have wanted to not have to solve for this. Also, full disclosure, I'm going to be showing you what's essentially a web admin interface for doing something like this at a very high level. This is by no means identical to the approach that one would recommend using for this in production, especially because in a case like this, your job isn't really to scale up when you get more load. Your job is to scale up every day at 5 a.m. and then scale back down throughout the day when you no longer need that level of API support and DB replication. So what I hope to walk you through is really the system by which you can reactively scale up systems on AWS in order to support intense load that is unpredictable, and in so doing get familiar with the tools and techniques on AWS's consoles. So any questions? Yes, sir. Go ahead.
The slides are white on black.
There's not really slides after this one. I'm going to be showing a web console, but it is mostly going to be a white background. Does everyone else want the lights down as well?
Yeah, it's the switch closest to you.
All right. Yeah, that one. Ooh, nice. Cool. Everyone get out back too. All right. Cool. It's a little faded too.
Projectors.
Projectors. Ridiculous. All right. So raise your hand if you've seen this, but not 5 minutes ago. Cool. Who can name 50% of these things and knows what they do? Cool. You guys are awesome. I feel like you'll be great contributors as we go through. So I'm going to talk you through a couple of services that we're going to be looking at and skipping over a couple that we're not. This is not really intended to give you an overview of how AWS automates deployment of servers for you at an even higher level. I really want to show you tools and techniques you're familiar with. These will be Linux servers, relational database servers, DNS routing, CDN, and all of that. So mostly sticking on the left side for a second. EC2, that's Elastic Compute Cloud, or it's cute. It's supposed to be EC squared essentially. So for Amazon, this is essentially the mechanism by which one is able to deploy virtual Linux servers or Windows servers or whatever kind of virtual servers you need, except for Mac, because that doesn't exist. Route 53 is their DNS routing system. It's a very robust and very cost-effective system for DNS when you want to be able to leverage the internals of the IP routing that happens on AWS. VPC, we're going to start there sort of in our exploration because it's sort of the EC2 2.0 in a lot of ways. It is the system by which Amazon has enabled you to have a private network inside their infrastructure. It gives you access to things like route tables and ACLs and internet gateways that you typically wouldn't see in a cloud hosting platform in the level of detail that they provide. S3 is a storage system. It's basically a put and get system whereby you can put a resource in a location at a URL and then pull it back down. Cloudfront is a CDN that uses edge nodes that in our frequent use case will suck data out of S3 and make them sort of like geo-distributable from AWS. So that's a pretty important part of keeping the cost down when you're transferring terabytes of data from your storage for something like Emacs that are big PDFs that you download. going to talk a little bit also about Elasticash, which is essentially a memcached or Redis backend in front of your application that you can use for doing highly available caching. RDS is a abstraction of database management that takes a lot of control out of your hands and replaces it with something that's kind of point and click, but gives you scalable database servers out of the box. And that is, pretty much what we're going to be talking about in terms of the services that you can leverage to take what's a pretty typical LAMP application and put it up in the cloud in such a way that it can reach more users without having to change your code base. So, any questions before we get started? Could I increase my font size on the browser? I'll try. I can't vouch for how well AWS is going to show you these things once we get into the interfaces, because they're pretty crowded and it's pretty complicated, and there isn't that much great documentation. So, with that said, anything else? Cool. All right. Let's start here. IAM. By the way, we're going to be looking at a lot of things that you could get away with not using. Technically, when you sign up for AWS, you have a root account that has access to everything. You can generate an access key and access secret for that account and never have to do anything else related to this. However, it's a really bad idea, and you should never do that. AWS gives you really granular ACLs. Who can fill in that acronym? I'm sorry, I've been using it. Cool. Oh, the two guys over there again. Great. Yeah. And access control list, exactly. So that is essentially a way that you provision access to individualized resources for individual users. Users are not necessarily people, and in most cases I would say they actually definitely aren't people. They're more like access roles. Those are provided through a user and group system in AWS that allows you to do something like register users. Here I've made a couple of simple systems where I have an asset manager. This is going to be a user that essentially has access to S3 for pushing and pulling data down. A queue manager, which has read and write access to the queuing system built into AWS that we're going to be using. And a server manager, which is capable of dynamically launching Amazon EC2 instances. These guys are then again organized into groups, and these groups are where we apply the permissions. So here's an example of the assets group. We'll see essentially we made an asset manager and put them in the group, and we gave them a permission policy, which is a template that we can apply to anyone in this group. Policy has a couple of things that are optional, a couple of things that are required, and what this is essentially saying is anywhere on S3, for all resources, you can do everything. So this is not actually how you would make it. You would be more granular. You would use the policy template generator. To show you what that looks like for a second, you can attach another policy and go through doing something like here. Oh, I can't scroll down because I'm all zoomed in. So the policy generator, when you don't want to type your own, which is pretty much always, you should essentially be able to say, for example, for the AWS Elasticash, I want you to be able to create cache cluster and create cache security group, but maybe not a parameter group and not be able to delete them. And describe events and modify cache cluster. So these are all documented and defined permissions that allow you to do most things. All actions is sort of going to be like the Elasticash : star that we saw in the template. With those applied, click add conditions, and you get something like, just like hide this because it's not important, and click add statement, and you end up with something like this. So there's a graphical representation of it, and then they will show you what that actually looks like, and you can add it in the following step. So that's more or less how we created that setup. I sort of skipped creating really anything because we would never get through the session in time because there's a lot of waiting involved in some of the following steps. Next thing I'd like us to look at really quickly is what database replication looks like in AWS. I wouldn't say that MySQL is a good example of the most robust data store that you could be using on AWS, especially if you have some really write-intensive applications that you'll see for big logging systems or really anything that has a lot of write-intensive traffic to begin with. But this is a great example of how there are cost-effective and sort of well-designed systems that one can put in place to essentially have like a master-slave system that's available to you for having a a database that you write to and maybe a set of databases that you read from. For those of you who are not totally familiar with the concept of what we're discussing, the idea of database applications is that one, scaling them is one of the hardest things you have to do, and probably the bottleneck that you will first encounter when you are trying to make a highly available application. especially as a design problem. And two, it is the nature of most applications that there's more reading than writing, basically. Reading is something that you do all the time whenever you get any data about yourself. Usually when you have a signed API request, you have to look up that user every time. Writing is really when you write or update content. It happens less frequently, and therefore it's possible to design an architecture where you have a couple of low-cost and easy-to-maintain read replicas that essentially are capable of selecting the rows that you wrote from the master with an acceptable amount of millisecond-level latency between them. That replication is a capability of MySQL that is essentially taken care of for you by RDS. So what we have here is a master-slave system where you have one database master and 3 slaves. A framework like Laravel makes that super simple. Over here, we'll essentially see a way that you can create a write host and an array of read hosts. Everything else, again, is in the framework. So this is a good example of something that can easily take advantage of that functionality. One other thing to note here is that these slaves are each made available in one of 3 regions in US East 1. There is a set of data centers in secret locations around the world, basically, that AWS manages, and within each of those you have these things that are called availability zones. A good pattern is to make your content available in as many availability zones within a region as possible, and wherever AWS will allow you to, enable cross-region load balancing in some way. A anti-pattern is to do everything in one region because you'll have slightly faster latency. So everyone sort of clear on, yes, sir?
I was going to say cross-region is great, but latency is bad. You can also do this between different ACs. Historically, they don't typically have full region outages. So there's only one to my knowledge. So that's more.
Yes, that's totally correct. At the same time, I mean, another interesting thing that was sort of told to me anecdotally by our account rep for AWS is that the locations of these places are so secret that their VP of AWS doesn't know where they are because he doesn't need to know, and he doesn't need to know. So, for example, there are stories that I've heard about people showing up at these things because they got the address from a lower level employee that wasn't supposed to give them for an inspection that wasn't announced, where the person who gave them the address got fired and the person who showed up is sanctioned, basically. So it's that secret where Facebook is a little bit more open about where they have places that you could theoretically bomb or set fire to in order to take out huge swaths of their functionality. AWS really locks it down. At the same time, so that's a totally valid point, right? But preparing for disaster is probably what we're doing here whenever we make a system that's more robust than it needs to be. So inter-region load balancing is what we're going to talk about, and it's actually the most reasonable thing you can do. Cross-region load balancing is almost impossible without you developing it all yourself. So with that said, yes, sir, Sequoia.
I had one question just for clarification between regions and zones. And my other question is, you're talking about spreading out your database server over multiple regions. Are you doing the same with your application servers? Because presumably if application servers are all in Northeast, why would you do a database server on West Coast?
Right, that is a great question. And what we're looking at is inter-region. So everything we're doing is in the North Virginia data center. Availability zones are different data centers within the same approximate region. Their latency is something like 0.005 milliseconds between them. So
you're saying within one region that you pick, you want to pick multiple availability zones, but the availability zone is actually
yes, exactly. It is it's a virtual data center as far as we're concerned. In terms of the network topology, there's almost zero latency between instances in the same availability zone, and negligible latency between instances in the same region but different availability zones.
So you're not talking about spreading servers out one on the West Coast, one on the East Coast?
No, but for disaster and recovery, that is exactly what you should do at the same time. Services like Cloudfront are actually handling the geo-distribution and caching of your data at the most appropriate edge node, probably around the globe. But in terms of database servers, which are a great example of things that you should never be accessing directly anyway, right? I mean, there's no reason that a database server needs a public IP address. Because as far as the network topology is concerned, what you need is a low latency connection between your actual application servers and the database. In the case of the application servers themselves, I mean, your load balancer is always going to be defined in a region and in an availability zone. But as far as they're concerned, they work nicely with different servers within multiple availability zones in the same region. We'll be looking at that specifically in a second, so if that's going over anyone's head. It might still go over your head, but we'll look at it in greater detail later. One thing that I want to touch on really quickly before we keep going is VPC. VPC stands for Virtual Private Cloud. Every system comes with a default VPC. I've gone ahead and named my things just so you guys can sort of see what those look like. They have a couple of notable things that we'll be discussing, one of which is subnets, which are by definition defined in an availability zone. So each of these things, which have a lot of properties, are essentially set up, one each in US East 1A, 1B, and 1D. A subnet itself has a route table. Typically, it has a network ACL as well, which says, allow internal traffic and deny external traffic. Finally, they have an attached internet gateway in many cases, which will allow basically instances created in these subnets, and these are basically allocation sets of private IP addresses for your own technology that you deploy inside AWS. That means that they can read and write from the internet. And it's worth pointing out that if you're outside of your default VPC or if you turn off this internet gateway, your instances can't read and write from the internet. And usually that's a good thing because you're building something that has no internet addressable needs and therefore shouldn't be on the internet because it's a security risk that you don't need to take. Route tables in many ways accomplish something implicitly when you have a default VPC set up like so. You can associate them with subnets, which will basically, take away their automatic public IP behavior and give them a more granular level of IP assignment, which is usually internal and gives you a little bit more control how those are addressable with private DNS inside AWS. Finally, really quickly, let's look at security groups, which are going to be defined across various VPCs and essentially give you a set of inbound rules that allow you to do specific things. So a common setup that you'll see is to whitelist all traffic coming in on port 80 and port 443 and to allocate specific IPs that have SSH access. What that does is basically give you the ability to handle web traffic very easily while still restricting who can shell into your servers or have any level of administrative control above the web interface, which is usually a couple of layers of proxy before it gets down to your application, which can access the DNS. So that's it for VPC. Unfortunately, we have 45 minutes, so we're going to have to just keep going and skip over things. SQS, which we'll be looking at, is a pretty great example of a robust system that allows you to do decentralized queuing of tasks that can be handled asynchronously. Anyone care to name some reasons that you might want to develop an asynchronous task in your web application? So Corey, you're first. What's up?
You're doing something that takes a long time, like disk writes or that.
Totally. Yeah, so that's how it can handle two things, sort of. Like if you have a set of worker servers and a set of application servers, let's say, you might want to set up a queue listener on one of your worker servers that implicitly throttles something that is a write-intensive activity. And what you benefit from doing that tangibly is that you can throttle it and you can handle it without impacting the request turnaround for the client who made an API request. So a really good example for that in the diagram that we were just looking at is subscribing for push notifications, which is something that actually happens right here. So this is like this connecting arrow from the queue and down to the push service. The reason I bring that up as a good example is that subscribing for push notifications is something that as the client, you don't know if it worked or not, and you don't care if it worked or not because that part of the application topology is not yours to control. As the API server, all I have to do is respond quickly and tell you, okay, that worked because I got your message and I pushed it into the queue. And then that write, which is a sort of API request that has associated latency, is now non-blocking essentially. So you can handle way more subscriptions that have intense writes, whether they're to a database or to another system, by queuing them and resolving them later. And anyone else have any other ideas? Sure. Okay, that's good, because I mean that covers like the main use case for what we'll be talking about. So in my example application, what I've done is I've sort of set up some relatively simple routes that looks like this. So this is the highlighted code right here. This is essentially a post to the data system that allows you to write a number of records that generates basically something inside a queue. These being enqueued in SQS means that basically there's no bottleneck associated with writing because what I'm doing is making the transactions work independently of the behavior of the the API request. So you can send as many of these as you want. If you get too many of them, the application is going to take care of throttling them for you. So I'll sort of show you what that looks like by opening up Postman. Does anyone here use Postman? A little bit? Postman is a nice client that gives you the ability to make a excessive number of writes through this post interface. It allows you to basically make any HTTP request you want. So it's a really good tool for testing your API as well. So what I'm going to do is just post to this endpoint, which is designed to write 10 records. And I'm going to get a quick message back that says queued writes. So that's basically what's happening here. The enqueuing means that it's kind of deferred, but it doesn't matter. So in SQS, that message is probably already gone because I have a queue listener listening. So it's in flight right now. It's going to resolve those as I go through. And when they're done, it's going to refresh the interface and tell me that they're done. Now, I don't know if that will happen immediately or not, but let's see. So, in the meantime, I can send like a million of these if I want. And I'm not going to see any heavy database load that actually impacts my ability to develop my application. And I'm going to be able to very quickly make a GET request, for example, to see my most recent 10 records. And the reason that that works is because these messages are being popped off one by one, and there's no impact on the front end, essentially. So that is how that system works, and that system works pretty well. Laravel, again, is sort of to the rescue to make us not have to show you how application code is developed to leverage the queues that are made available, because they have a configuration that looks more or less like this in production. I say use the SQS as a default connection, put in the key and secret and the queue endpoint like so, and everything else is just going to sort of handle itself for us. So that's a really nice thing that we like about frameworks like Laravel. They have convenient abstractions for things like this that mean you don't need to be an expert in order to take advantage of them. Finally, I'd like to sort of turn to what the application architecture looks like, for the actual application servers, which is probably the thing that's nearest and dearest to people who deploy things all the time. So in the topology that we're looking at, I'm going to have a couple of instances. It seems to not work well at this Zoom level. So what I have essentially in front of you right now is something that I'm calling a launchpad, a development server, and an auto-scaling group. Let's go through these one at a time. This development server is essentially a Linux server that I have deployed on AWS. What it has is a image that essentially contains all of the dev, staging, and production environments that I ever might want to launch for my application. This server is actually what's going to be resolved through my load balancer to my dev and staging instances. For the purpose of having a convenient and consistent topology, I'll usually put dev and staging behind a load balancer as well. Even though those aren't actually receiving heavy load, it's helpful because then they have the exact same topology. So let me shell into the launchpad and show you exactly what we're looking at. I'm doing it. I'm already on it. There you go. Is that readable enough?
That's good.
All right, cool. So we'll have essentially dev, production, and staging. In our typical environment that we'll have, we'll want to use a combination of on-server caching that allows us to manage sort of distributed purges to something like Varnish, which is an accelerator that stores on disk and/or in-memory cache of your endpoints that are highly cacheable. For an application like a mobile application, typically you'll have something like instance metadata, right? That will have something to do with like this is the name of the application, this is the URL of its CDN, these are the names of its base objects, and these are let's say for example like the taxonomies that you can use to filter events, like for like an event-based application. Those are the sorts of things that are going to change about once a year or never. So we cache them very aggressively. We have no disadvantage from this approach, and it works very well. And it means that we can handle a lot more load out of the box. So what this sort of looks like is, for those who are familiar with Apache 2.4, or there's nothing special here anyway. Basically, have something that looks like like a dev.conf, which is a really simple virtual host that we have set up listening on port 8082. These just have a document root and directory, and everything else runs off of mod PHP. Server name doesn't matter because that host mapping is actually handled by Varnish internally. If you look at Varnish, Varnish is a great tool that everyone should use if you get an opportunity to. It will really make your applications faster and help you design things better while it's at it. It uses this thing called a VCL that basically tells you what the listeners are for the different backends of the various ports that we make available. And then we have like these, Sorry, what? Yeah, everyone hates VCL. So
Let's see, this sounds great.
Yeah, exactly. So like, and the reason everyone hates VCLs is because they're scary. Like, what they do essentially is compile into C code that gets then compiled itself into bytecode that runs on the server in real time. The advantage of that is like these things can take like 40,000 requests a second without blinking on like some of AWS's cheapest infrastructure. And it's doing like regex matching with something like like 5 if-else conditions. So it's super awesome that something like this exists. It also sort of handles RESTful caching for us. For the purpose of the final examples that we'll be looking through, I set up cache control headers essentially so that they tell Varnish not to cache anything and to cache certain things very unaggressively. So basically, like the record data can be as recent as 5 seconds before you have to get it not from the cache. Post requests, which are typically going to be writes or updates, are going to never be cached by Varnish unless you teach it to. But anyway, yeah, it is a weird and arcane syntax, and I would say Google is your friend. Another thing that's really nice about it, or unfortunate about it, depending on how you look at it, is you can basically run your config through the compiler and test it, and then see what comes out in terms of the actual compilable code. So that is helpful, at least to not restart Varnish if there's an error. So just to show you like why it's incredibly dangerous. Like if I just decide at some point that I want to put A equals there or something, nothing's going to stop me from doing that. So it's going to stop it, and then it's going to start it again, and it's going to be broken, and now I'm panicking, and my production is down at this point. So be very careful with Varnish when you use it, because it is a tool that's easy to abuse. Anyway, so with Varnish in front, essentially we now have a system in place where we have a listener on port 80. Deep down in this Ubuntu distribution that I'm using, there is a Varnish config that does stuff like tell it to listen on port 80 and forward things accordingly. Let's look at the load balancer now to see what that's actually doing. Over here on my load balancer, which I have to scroll down for again, sorry. I've set up a launchpad, which is essentially passing through my dev and staging environments, and I set up a production instance as well. So let's look at the launchpad first. The launchpad is essentially configured in such a way. It has a DNS name, and I can make C names through Route 53 over here on my illustrious personal domain, which has record sets that essentially say for dev and for staging, what I'd actually like you to be doing is routing an A record alias to the internal load balancer. So this is a super fast and succinct way that you can point DNS names, like C names essentially, as aliases to load balancer instances. Inside of this, what I essentially do is I attach an instance like so. I click Edit Instances, and I check off the ones that I want to have in there. Everything else related to the host mapping and the configuration is handled, thereafter by the instance that it lands on. A couple of really important things to understand about what we do here. We are going to have configured a health check, which basically hits port 80 on index.html. Varnish is taught to ignore the host name and just map it to a file in a way that makes sense for this. The way this works is if my instance becomes unhealthy and therefore inaccessible, this could be as simple as I wrote my application badly and the server is has a memory leak and it's crashing. It could be as complicated as I can't handle the CPU intensive requests that I'm receiving at the current rate right now. So what it's doing is basically every 30 seconds it's going to ask for index.html. I'll just use the public DNS for this development server for a second. Go to index.html, it's a ping, it gets a pong. So that's it. That's the only thing that it's doing. It tells me that Apache is up and Varnish is up and they're working well together. So that's, not really a robust health check, but it's enough for the purpose of this example. You might want to do something a little bit more health checking related to your actual application in production. Finally, monitoring is set up against this that allows me to see exactly how many requests are passing through this load balancer and what's going on. Security groups are applied to it, saying essentially, the same security group that says, hey, port 80 traffic is valid is applied here as well, which means that, web requests through a browser without specific IP whitelisting get through. And that will pretty much tell us on listeners, what's happening. I'm passing port 80 to port 80. Let's look at production. It's pretty much the same thing. One thing is going to be very different, which is I'm passing 443 to port 80. Anyone have any guesses about what's happening there? Scoria, you're so helpful. Thank you for raising your hand. What's up? Yeah, exactly. So the advantage of this is that, you know, one, SSL negotiation is complicated and very CPU intensive. So under HTTPS load, you actually have a different scaling problem on your application server if you're doing the decryption there. So with the secure and tight connection between the load balancer as the front end and essentially now the application server as the back end for those requests, you can have AWS manage your certificates and swap them out all at once. The other thing that makes this incredibly awesome is that if you have a server farm that has like 20 servers and your certificate is set to expire, you go and point and click and change the SSL certificate. It's that simple. Trying to find the edit button down here. So basically here, you know, my SSL certificate is my load monster certificate that I made. I can click change and change it, and then it will just, you know, sort of work out of the box. In particular, that means here on Postman, you know, this request that I made was by HTTPS, and it just works, no problem, nothing to worry about. And that is sort of like, you know, an important thing to understand about how you can have securely deployed applications and have the load balancer do the brunt of the work and also give you a good abstraction of how that certificate is installed. Yes, sir.
Can you set like an HTTP header for like exported protocol?
Yes, yes, and you know, especially if you're like, if anyone does anyone use like mod PHP and Nginx or sorry, PHP FPM and Nginx in front of applications? Yeah, so you have to do that, and it's not going to do it for you. So X forwarded IP to get the real IP address that was forwarded for, as well as the X forwarded for itself, and X forwarded proto, all important and all necessary if you're doing that. My Apache example is great because it does it for me, so I'm happy with that, and that's sort of one of the nice things about how Apache handles itself, because it's not a reverse proxy in the same way that Nginx is, so it has a lot of magic inside, which is real convenient. All right, so let's sort of like go into the nuts and bolts of like where things get really interesting, in my opinion. So launch configurations are essentially a template for launchable instances on AWS. An instance is, you know, an actual running server that has an internal IP address and maybe a public IP address. Another thing that's unique about it is that it's configured just the way you like it, and it runs your application correctly. So typically what you'll do is you'll make a production candidate, which is something like what I'm calling here a launchpad. And you will make it set up in such a way that it handles your production traffic exactly the way that you want it to. And then what you'll do is you'll essentially right-click it and say create image, which is not available from this menu because of my zoom level. If I back it out for a second just to have access to it, I can create image. I'll zoom in again. If that's me. It won't. Good. I think it's disabled my, my command key or something. So essentially what you do is you assign an image name, and that is about it, and you click create image, and it's going to go ahead and create that image for you. It uses a minimal amount of storage that you will be billed for to have these images, but they are basically not your problem. Notice that my SSH just started freaking out because I got kicked out of my launchpad because it shuts it, it reboots it basically for a second in order to create the image. So having done that, I will actually have a valid AMI that I already created, which is my what I'm calling my launchpad v1. Now, note that I have these as T2.micros, which are one of the cheapest instance types. They give me reliable burst performance and mostly are slow and crappy, but good enough for the purposes of this demonstration. My advice to you would be keep a launchpad and deploy to it, and then create images and work their way into your load balancer. That way you don't ever have to take your application down to make an image of your production instance. It's a great pattern. It works really well. There's not really any overhead associated with it, and you can write scripts to automate it for yourself very easily. Because, by the way, AWS has a CLI or command line interface basically for anything that I'm about to show you and have shown you so far. And part of good automation is really being able to like, press a button that deploys code for you and servers for you eventually. So my development server is where I'm actually deploying my dev and staging code, and that's more flimsy and more likely to change and has less aggressive caching because that's not really what I'm after. My launchpad is ready to be production. Like if I put it in my load balancer, it would serve production traffic just slowly because it's probably on a cheaper instance type. These things, they run for something like less than a cent per hour. Basically for pennies per month, you have the this perfectly and constantly available deployment platform. Launch configurations are pointers to images, which are taken from your launch pads. Here's an example of one that points to an AMI. That's the Amazon machine image. It uses a key, which is essentially a private key that you get to download once, that it gives you SSH access if you need it, although if it has a public IP, that's irrelevant because you still can't get in except through your internal VPN. with the launch configuration, one is essentially able to make these great things called auto-scaling groups. And that is sort of the final and most important piece of our conversation. So for this load monster example, I have an auto-scaling group, which basically is set up as follows. In its launch configuration, it basically points to a launch configuration that I own and have created. It also allows me to do things like have a desired min and somewhere down here max number of instances, and this sort of goes back to an earlier question from Sequoia. I point these things to subnets, which in turn point to the actual availability zones, or defined inside availability zones within a region. And now it is responsible for deploying within these different subnets and making instances, pretty much evenly distributed across these availability zones. So a good pattern there is that, if there is a problem in an availability zone, which does happen from time to time, although not very frequently because AWS is very robust in that way, I have no impact whatsoever on my application infrastructure. So especially if you make a rule like I'm going to run a minimum of 3 servers, you're likely to have 1 in each availability zone. I'm going to go ahead and change that right now and save it just to show you what actually happens. My maximum group size. There we go. Thanks. I'll set my maximum group size to like 20 to allow it to do whatever it needs to. All right. So desired 3, 3, and max like so. This little info icon is now already telling me instances may be in a pending state because they're in the process of launching them to meet my desire that I've expressed through my configuration. At this point, let's go over and look at what the instances are. You'll see that we have 3 instances. 2 of them are in the process of launching. 1 of them was already there. It's the production that we were just looking at. And these are, very soon going to be capable of receiving traffic from my application. So this is, in a nutshell, and in a very simplified form, the essence of horizontal scaling. I've basically said that now instead of having 1 cheap server that's handling all of my traffic, I now have 3, and these 3 can more or less equally in a round-robin fashion, which is handled both for HTTPS negotiation and for the actual request servicing by the Elastic Load Balancer, which is now the entry point for my application. Everything that relates to scaling happens at a higher level of abstraction, and I no longer have to worry about what each server is doing. That's why a typical rule of thumb is if you ever have to SSH into your production servers, you're doing the automation. And in general, our rule internally at Fuzz is that we don't ever go to production. We only ever look at our launchpad to see what's happening. We capture our logs through another queued service, and we actually don't ever want to look at those servers because it's dangerous if we can get to them from a computer, and we would rather not. So these are in the pending state. They'll be available very soon. They have to boot up. It takes, okay, so they're already in service right now. That means they've passed their status check, and they're ready to start serving traffic. Final thing to look at, which is very important, is scaling policies. So what you see here is essentially a set of rules that I have made that track within my Elastic Load Balancer thresholds that create something called alarms that are telling me when I should add or remove instances automatically. When you get this piece of automation in place, it means that if you deal with traffic spikes where a lot of people come to your site at a certain amount of time, but most of the time nobody comes to your site at all, like you send a newsletter, for example, and suddenly you have a lot of traffic. Rather than changing your desired and minimum instances to suit your purposes, what you can just do is execute this policy when it reaches this alarm threshold like so. So what I've said is like when you get under 500 requests as a sum for an average of 60 seconds, for this load balancer, remove 1 instance because we don't need another instance to serve that much traffic. And I have a similar one, which is a little bit more aggressive, that says when it's greater than or equal to 500 requests per second, requests per minute, I'm going to add 2 instances and then wait 120 seconds before allowing another scaling activity. So those 2 pieces in place basically make it so that I'm arbitrarily able to apply new instances to my cluster based on real-life load conditions without having to touch this. So in production for big APIs, for apps that do something like floods of traffic that look like tens of thousands of users per minute, we do exactly this. And then we sleep easy at night because nothing ever goes wrong. It scales itself up when it needs to and scales itself back down when it's done. The best part is that it's really cost effective because it's all on-demand pricing, right? So those additional nodes that go into our load balancer essentially have no relevance to the overall monthly bill because they're on for all of 5 minutes and then they turn themselves off. So it costs us a couple of cents, we service all of the traffic, and move on. What's up, John?
You're getting reports of when that happens?
That's a great question. So to tell you the answer, I'd say, there's one thing that we can do is create a notification. These work through SNS, and they're kind of fancy. So I would have to create a topic like so, like notification cluster. Whenever instances launch, terminate, fail to launch, fail to terminate, and like so. Sometimes you need to know when you're like experimenting and trying to figure out if your load balancer and your auto-scaling group is doing enough. Other times you don't. This is an invalid topic name, probably because I'm not sure if I need to create it or not. Okay, there's no spaces. That's how helpful AWS is, by the way, right? They'll just tell you something went wrong. There's like no error message at all. That's how they roll. I mean, they're into building infrastructure tools. They assume that you're smart enough to figure it out, and they also, somewhere will provide docs that will be helpful. Oftentimes you can inspect the JavaScript error in the console to see what really happened there. So anyway, we're literally out of time, which I find to be regrettable, but I hope anyone who wants to ask any more questions or stick around feels free to. The thing that I didn't show you that I really wanted to, which would be super cool if we could get through it in this time, is essentially a Apache Benchmark that is going to trick my server into thinking that it's in a panic scenario. I made an endpoint that basically base 64 decodes the base 64 encoded OpenSSL random pseudobytes to the tune of 10 million characters. And tells it never to cache, right? So the point, and then it like gives you a message, right? So in the simplest example, if I just load monster /read, right? Like basically this is going to work a little bit, but it's going to take a little bit of time because it's like cacheable, not at all. And it requires CPU activity. So you could attach this to any number of metrics. What I'm going to do is, tell it with a concurrency level of 150, make 1,000 requests to this endpoint. The first 200 already succeeded. The next couple are not so much going to. It can be super interesting when that happens. Meanwhile, what we can monitor, and I'm about to get like a bunch of emails in my pocket probably from that notification I just set up, is the scaling history, right? So far it knows that it launched a couple of new EC2 instances. Meanwhile, over in Cloudwatch, where we have an exciting level of interactivity with these reports, we can see what the historical metrics are for these as well as what's happening right now. So it doesn't want to load right now. Refreshing. So basically, all of my alarms are hidden, and that didn't work. Hold on a second. AWS is a little bit confused right now. Insufficient data may be on too. Oh, okay, so it says it doesn't actually know what's going on right now. That's not real. I think we're just having some issues. Okay, so you see the scaling history essentially. So this is the 500 threshold, and we've already seen that it just spiked above it in the last couple of minutes. So if we look at the history here, it's going to say alarm updated from OK to insufficient data. Within a minute, that's going to resolve itself, hopefully, to the alarm state of CPU low. Not what we were quite expecting to see. CPU high, insufficient data to OK. Well, it's not okay anyway. It'll figure it out eventually. I'm not sure if it will do it while you're sitting here, but eventually, as these requests continue to go through, it seemed to quit because I had too many open files, possibly. Goodbye and thank you. Eventually, this thing will go into alarm mode, and the second that happens, it's going to start spinning up instances and popping them into my load balancer the second they become available. And that is the essence of auto-scaling and the way that you can take your hands off of it and have an application that scales out to tens of thousands of users. So that's pretty much my presentation. Thank you all for attending. Any Any questions or comments? Happy to receive them for the group or just after the session. Thanks for coming.
Laravel decide which read database.
ArrayRand.
What's it?
ArrayRand.
Is it randomly?
Yeah, it's a piece of shit. I'll show you. There's a function called get read write connection. Get read write config. So that's literally the code. It's really not robust at all. Yeah.
Load balance?
Well, that's what you're doing essentially. It's just like, instead of having a round robin, you're looking at this pseudo random int that's inside PHP. So Yeah, I will soon.
Thank you.
Thank you.
Yeah.